Hello everyone, my name is Aryan and today I am going to discuss problem based on unbiased estimator. As in my last lecture, I have discussed about concept of unbiasedness and one problem based on the unbiasedness. So today I have one more problem and I have mentioned here the problem and its solution. So now come to the problem. Now you can see here, let x1, x2 and so on xn be a random sample from a normal distribution with mean mu and variance sigma square. Then question so that sample mean is an unbiased estimator of mu. Mu means population mean. Okay. Second question is capital S square. That means this is 1 upon n summation of xi minus x bar square is not an unbiased estimator of sigma square. Sigma square is population variance. And third one is n is square upon n minus 1 is equal to 1 upon n minus 1 summation I going from 1 to n xi minus x bar square is an unbiased estimator of sigma square. And fourth one is s square is asymptotically unbiased estimator of sigma square. And last question is s square upon n minus 1 is an unbiased estimator for the variance of sample mean. So okay, so in this problem we have 5 parts. So come to the solution for the first part. In given question, we have x follow normal with mean mu and variance sigma square. So we can write it xi follow normal with mean mu and variance sigma square, where I going from 1 to n. Is it clear? Okay. So if xi follow normal with mean mu and variance sigma square, then we can write it expected value of xi is equal to expected value of x, which is equal to mu, and variance of xi is equal to variance of x is equal to sigma square. Okay, now come to the first part. First part is what? Sample mean is an unbiased estimator of mu. So sample mean is what? Capital X bar. So taking expectation of X bar and then simplify this term. X bar is what? 1 upon n summation of xi and taking expectation inside and 1 upon n I going from 1 to n expected value of xi, and we have value of xi is what? Mu, and this summation becomes n, so n is cancelled out, resultant is mu. Okay, and by definition of unbiasedness we know that if expected value of the estimator is equal to the population parameter, then estimator is called unbiased estimator. So now you can see here expected value of this quantity is equal to population parameter. So we can conclude that X bar is an unbiased estimator for population mean mu. Okay, so this is the first part of this problem. Now move to the second part. Okay, so come to the second part. Second part is expected value of S square is equal to expected value of 1 upon n summation of xi minus x bar square is not an unbiased estimator for sigma square. Okay, so now you can see here 1 upon n summation of xi minus x bar square, we can rewrite it like this, just simply adding mu here and subtracting mu here in this expression. Okay, now then again simplify this expression. 1 upon expectation sign expected value is outside, 1 upon n summation I going from 1 to n. First term is xi minus mu and second term is x bar minus mu. Just taking minus outside, then you can write it x bar minus mu and whole square. Okay, now open the square of this quantity. So first term square plus second term square minus 2 times of first term into second term by formula. So now you can see here what we have. Expected value 1 upon n I going from 1 to n summation xi minus mu square plus x bar minus mu square minus 2 times xi minus mu into x bar minus mu. Then take summation sign inside. Then what we get? 1 upon n summation xi minus mu square first term plus summation x bar minus mu square second term minus 2 times x bar minus mu into summation I going from 1 to n xi minus mu. Okay, is it clear? So again we can simplify this expression in form of next equation, and now you can see here first term is as it is we are writing here. Second term is what? This is constant term, x bar and mu both are constant, so that's why I going from 1 to n becomes n. So this is n x bar minus mu square. And similarly, now you can see here, this is 2 times x bar minus mu. So we are writing 2 times x bar minus mu one quantity, and second one is what? I going from 1 to n xi minus mu. So I going from 1 to n xi is what? N x bar, and minus I going from 1 to n mu is what? N mu. So take n outside, and it's this quantity is becomes what? X bar minus mu. So that's why we are writing here 2 times n x bar minus mu square. Is it clear? Okay. So come to the next step. So this is positive of n x bar minus mu square, and this is 2 times of negative n x bar minus mu square. So it becomes minus n times x bar minus mu square. So we can write this expression in form of next expression. Expected value 1 upon n summation I going from 1 to n xi minus mu square minus n times x bar minus mu square. Is it clear? Okay. So come to the next step. 1 upon n taking outside, and we are taking expected value inside. So summation I going from 1 to n, first term expected value of xi minus mu square, okay, minus second term is what? N this one, and 1 upon n taking inside. So it becomes 1 upon n, 1 and n is cancel out. So x expected value of x bar minus mu square. Okay. Now we know that this is what? This is variance of xi, formula for the variance of xi. So in place of expected value of xi minus mu square, we can write it variance of xi. And what is this? This term, expected value of x bar minus mu square. That means this is the variance of x bar. Okay, as per variance definition. Okay, now you can see here we have the value of variance of xi, and for the variance of x bar, we can simply find out the value of variance of x bar. Now you can see here I have mentioned. So variance of x bar is what? Variance of 1 upon n summation of I going from 1 to n xi, and then take 1 upon n outside of the variance, so it's become n square. Okay. So summation I going from 1 to n is what? N, and variance of xi, and value of the variance of xi is sigma square. So n and n cancel out. Resultant is what? Sigma square by n. Is it clear? So now we are putting the value of variance of xi here, variance of x bar here, and we are getting the resultant is what? Variance of xi is sigma square. Summation I going from 1 to n is what? N, and denominator is n, and n cancel out, minus variance of x bar is what? Sigma square by n. So sigma square minus sigma square by n, it becomes n minus 1 upon n sigma square. Okay. So now you can see here expected value of s square is equal to n minus 1 upon n into sigma square. That means it's not equal to sigma square. Okay, that means this is not equal to sigma square. Okay, so now we can conclude that s square is not an unbiased estimator for sigma square, because we know that if expected value of estimator is equal to population parameter, then we can call it unbiased, otherwise not unbiased estimator. Okay. Okay, so third part is n s square upon n minus 1 is unbiased estimator for sigma square. So now from equation number 2, we have expected value of s square is equal to n minus 1 upon n into sigma square. So we can rewrite this equation number 2 in form of next step. So taking n minus 1 upon n left hand side, it becomes n upon n minus 1 expected value of s square equal to sigma square. So we can take n upon n minus 1 inside expectation. So it's become n upon n minus 1 into s square is equal to sigma square. That means this quantity is unbiased estimator for sigma square by definition of unbiasedness. This is our estimator, and taking expectation provide the population parameter sigma square. Is it clear? And this quantity can be written as in this form. So you can say that this equal to this, that means this is also an unbiased estimator of sigma square. Okay. Is it clear? This is third part, and come to the fourth part of this question. Again, we will use this equation number 2, as we have expected value of s square is what? N minus 1 upon n into sigma square. So we can write it 1 minus 1 upon n into sigma square. Okay. So taking limit n tending to infinite, expected value of s square. So if we are taking n tending to infinite, then second term becomes 0. So resultant is what? Sigma square. That means if we are taking n is infinitely large, then s square becomes unbiased estimator. That means s square is asymptotically unbiased estimator for sigma square. Is it clear? Asymptotically means n tending to infinite. Okay. Now move to the fifth problem or fifth part of this problem. So now again we are using here the equation number 2. So we have expected value of s square is equal to n minus 1 upon n into sigma square. So we can rewrite it in form of next step, expected value of s square upon n minus 1 is equal to sigma square by n. So now you can see here s square upon n minus 1 is unbiased estimator for this quantity. Is it clear? Because expected value of this quantity is equal to sigma square by n. That means this is unbiased for sigma square by n. So you can rewrite this term in form of 1 upon n into n minus 1 summation I going from 1 to n xi minus x bar square. So this is an unbiased estimator for sigma square by n. And sigma square by n is what? Sigma square by n is the variance of x bar. Okay, so now I think everyone is clear the concept of unbiasedness and also the how to solve the problem based on the unbiasedness. Okay, so thank you so much to everyone for watching this video, and in my next lecture I will join you with second property or second criteria for the good estimator. Okay, so thank you so much.